Now let's take a look here at example number 3. We can see here that we're working with the type 1 improper integral that has bounds going from negative infinity to positive infinity, essentially meaning that we want all of the area underneath this curve. So if I was to sketch out a picture of this curve, I would see that I get some sort of a shape that looks something kind of like this. And again, I'm interested in all of the area. But we can't compute this directly. What we saw in the previous definition is that I have to kind of establish a blue portion and a green portion of this integral. I kind of got to split it into a couple pieces. And remember, I can choose to make that split wherever I want. Now, for the sake of simplicity here, I'm just going to choose my split to be right at 0. I'm going to have a left half that's all blue and a right half that's all green. And so I'm going to separate my integral out then in the following way. I'll say my integral here is going to turn into an integral from negative infinity to 0 plus an integral from 0 to infinity. And hopefully you can see which one of these integrals corresponds to each of the individual parts above. Now, of course, each of these integrals has to be evaluated separately. I'm going to have to imagine that in the green, there's going to be some value of t, and I can find an area from 0 to t. That's doable, and t is going to need to be moved up towards infinity. On the other side, though, I might need another variable. Let's call it s. And I know I can find the area from 0 to s, but I'm going to have to slide s down towards negative infinity. So when I set that up, I'm going to have here a limit as s goes towards negative infinity, integral from 0 to s, 1 over 1 plus x squared dx. And then I'm going to have my limit for my green portion. So that's going to be t going towards infinity, integral from 0 to t, 1 over 1 plus x squared dx. If I want to evaluate each of these limits, notice I'm doing them separately after I complete those integrals. So let's see. I'm going to still have my limit, s goes off to infinity. And notice that my antiderivative of 1 over 1 plus x squared is actually just the arctangent of x function. So I'm going to set this up. Oops, this should be a plus. As t goes to infinity. And here I'm going to have my arctangent function of x from 0 to t. So I'm going to have to evaluate both these limits once I can see what I'm working with on the inside. Notice that the arctangent of 0 is actually just going to be 0, which makes this really easy to work with. However, even if I didn't have selected an easy value like 0, that wouldn't have made the arctangent so easy to compute. We'll see here in just a moment that everything would have still worked out very simply. Notice over here, I'm going to have my arctangent of t, and then again, arctangent of 0 creates 0. So interestingly here, what I'll see is that I got arctangent of 0 that would have been positioned right here, and I got a negative arctangent of 0 positioned right here. So even if I had no idea what the arctangent of 0 actually was, they would still cancel out, which is why it's so easy to make this split, or this separation of blue and green, at any real number that I want. Now, 0 here, of course, is convenient because it allows us to simplify down very quickly and just think about the limits of our arctangent function. Now recall that your arctangent function looks like this, and it levels out. It's got two horizontal asymptotes on it, one that occurs at pi over 2 and another at negative pi over 2. So notice here, if I'm interested in what happens to the arctangent function as s goes off to forever, I would be approaching pi over 2. Leaving the negative in front, I have a negative pi over 2. With my other limit, I'm going to again be approaching, here pi over 2. Oops, sorry, I lost my negative somewhere. This should be a negative infinity, excuse me. So I should really have negative because I'm subtracting here, negative pi over 2 plus a pi over 2. And of course then that leaves me with pi over 2 plus a pi over 2, and I get a final value of pi. So the total area under the curve up above is pi. And so this integral is convergent.